So.
I was just like, really all 10 of the last.
Yeah.
So it looks like it's mostly.
I got already for like second prep, but then I got just like the first game. Like those.
Oh, no, you just search it. You just searched it now. They, because look at Mary, Mary wrote in the second side.
Okay.
And the side of the version, you just say, she wrote a second, so what?
That would be a problem. You just door to door.
Yeah.
Yeah. Full Dixon, and you close. Cause why are married or younger?
In the book.
Oh, he caught more of it. It's just like, yeah.
I haven't asked someone before this because I wanted to take in person, but the person is off campus at the research park, and it's just like 15, 20 minutes away. I don't really wanted to go back close to that. So I took it online, but he puts us in do like our basically like on a screen, like it'd be like flexible up to the projector screen. So everybody can see.
These are like the only.
I love that.
Make all your folders.
But you know, it's got a driving back and forth.
So. You've been notes.
So.
I have to do it on Fridays anyways, seminar, but I have to get there at like 9 AM. Get on the shuttle after the class to get here, get on the shuttle and get back, then drive to Jack. So I'd be getting there at like, you know. Water. And drive home, then drive to Kansas first thing. I don't think so. I would just take it off.
Get the green.
Great fun, color, yeah. So going from.
So here's this. Here, it's usually.
This.
Okay, let's get started. So I hope the online version of the lecture worked out okay. Are there any questions from that? Okay, well, let me know. What we did last time, hopefully the online version that you saw got you going, thinking about flows and fluxes, and then primarily the water balance. We're going to keep going with that concept. That's a concept we'll use through the class in various different ways. So today I want to show you an application for kind of a large scale application of the water balance principle. And so here's some things that hopefully you'll learn from today: how to set up a problem using the water balance, and how to solve it and check it, and then how to apply it at different scales. So here we are. This is the there's Clemson in the Savannah River watershed, and that'll be one of the regions that we'll use for doing water balance. So here's the basic approach. When we apply a water balance approach to solving a problem, what we'll do first is define a region where the balance holds. So sometimes this is called a control volume. And we'll draw it around the region where the balance applies. And then we're going to identify things, processes that cause, in our case, water to go into the control volume, to go out, and then processes that cause the water that's stored inside of the volume to change. And we'll identify what those are. They have to cross the control volume surface. And then we can write an equation that says what's going in has to equal what's coming out plus the change in storage. We can write it as a mass balance, where the mass in is the mass out plus the change of mass stored. We can write it as a rate. So the rate of mass going in equals the rate going out. If the density is the same, and we'll often assume that for water, then we can do the volume going in, the volume going out, or the volumetric rate going in. That'll give us an equation where we get the left-hand side is the stuff coming in, and the right-hand side is the stuff going out, plus the change in storage. That'll give us a relationship between these variables that we can use for something. There'll be a variety of applications, but that'll give us it'll give us a relationship between the variables that will be useful. So here's the way that it works. We're gonna have we'll draw some sketch, and a sketch that I'll often use would be the cross section of a watershed, and we'll identify a region of interest, and we'll draw the control volume around it. So maybe it's this entire region, and so we draw the control volume like that, and then we come up with the problem will give us fluxes that cross the boundary. So we'll draw those in, some coming in, some going out, and then some change in volume stored. So something going in, something going out, and then change in volume stored. And then we can write the equation that in equals out plus the change in volume stored. That's the basic idea. And you saw last time we can do this with masses and rates. And so here's my little animation that is basically saying the same. Okay. So simple enough. One of the things, though, that we need to keep in mind is that only quantities that cross the control volume boundary will enter into the equation. If they're moving around inside of the boundary, they don't count. That's just internal mixing, or that's internal stuff, and can't consider that with this approach. One thing too, we need to make sure that we're using consistent units. So we can use mass rates, volume rates. We can use fluxes too, if the basic balance is going to hold for volumetric rates. For I meant rates, like constant density. If we take those rates and normalize to the same area, then we'll get a flux. If we do that, then the balance written as a flux will also work. But we have to keep in mind that it has to be normalized to the same area. Okay, so those are the rules. And then we can solve it. So here's the sketch that we have with the different fluxes. So the approach that we're going to use is we're going to keep this in mind. And we talked about these on day one, what these different terms are: evapotranspiration, infiltration, subsurface storm flow, overland flow, precipitation. This is the riparian ET and the direct ET. Probably just lump those into ET for our purposes. Base flow, groundwater flow, recharge. So what we're going to do is draw a sketch, draw in the fluxes that are important to our problem, and then draw in the boundary. So the first example will be for a watershed, and that's the boundary. So let's do it. So we have a okay. So there's the sketch. Now, if we have a problem that is involving the precipitation, ET, and runoff, these are the major fluxes in the watershed. We draw the control volume sketch like this. So these three are crossing the boundary. These are just internal, so they don't really count. And then the boundary or the equation is that P, which is coming in, equals ET plus the runoff going out. So that's the basic equation, and then depending upon what we need, we can solve for one of these terms or whatever. Okay, so that's the approach. And here's an example of this approach done at the continental scale. So I just drew that sketch on the watershed scale, but we could do something similar for the continent. And we would have precipitation coming in, evapotranspiration coming out, and runoff at continents. It'll be runoff to the ocean. And if we do the volume balance, then here's the volume falling on Europe as precipitation in thousands of cubic kilometers, 8.3 thousands of cubic kilometers. We normalize by the area of Europe, then we get 790 millimeters. So this is much easier for me anyway, conceptualize. So we have about, I don't know, about that much rain annually on Europe. And then ET is this, and runoff is that. So a convenient way to think about this is to take this is coming in, and these two are going out. So you take the volume that's coming out and normalize it to the precipitation coming in, and that gives you this column. So this is the fraction of the rainfall that is being evaporated and the fraction that is going off as runoff. It's also just, this is convenient because it allows you to, I don't know, these are simple numbers to think about. And it gives you a way to think about how the rainfall coming in is partitioned into evapotranspiration and runoff. So what we see in this table so let's see. Precipitation coming in, and then here's the ET coming out. So let's just look at the fractions here. So in Europe, we have 0.64% of the rain, or 64% of the rain coming out as ET. There's 56, 55, 57, 65. So this is the anomalous one. Everything else is around 55 to 65. And here, this is the high, and it's Africa. And, you know, Africa has the large Sahara Desert with high ET. So that's why this one is anomalous. But for the most part, all the other continents, well, here, actually, this is another anomalous one. Antarctica, it's 0. That's really anomalous. That's because it's so cold there that there's very little evapotranspiration. The others have pretty similar values, and there's the average, the global average. And as it turns out, that's just pretty much what it is around here. So ballpark, evapotranspiration is about 60%, maybe 2/3 of the rainfall. And then this is what remains. So here's the average, the global average, 0.39. And you see from there's an anomalous one, Antarctica, and the rest of these, here's the anomalous one, also here Africa. So Africa's got a little bit higher weight on evapotranspiration than the rest of the continents, but this is the typical distribution that we see between evapotranspiration and runoff. Another useful statistic here is the total rainfall. So there's the global average for rainfall, annual rainfall on continents, 0.8 meters. So about like so. And you can see we've got 2 outliers. Antarctica, where it's really small, and then South America, where it's twice the global average from the Amazon basin. Okay, so these numbers, I mean, there's a lot of numbers here, obviously, but these averages, I think, are useful to put into your knowledge bank. It'll give you a way to estimate what the ballpark rain would be in an average case, and then how it's distributed. So we have this pie chart here. If this is rain coming in, then we've got about 2/3 of it as ET and about 1/3 or so, maybe 40% as runoff. This is going to be important because this piece of the pie is what goes into the hydrologic cycle that we'll be interested in. This is just going back into the atmosphere right away, so it's not going to be circulating around as slow. Okay, so that's a perspective to start. Let's use this for some problems. Okay, so here's an example. So we have the average precipitation in the River watershed is 60 inches per year. The average discharge expressed as a flux over the watershed is 22 inches. And what is the average ET flux? Okay, so we're given precipitation and runoff, and we want to get ET. So these are the things that we're given and that we're after. So what we do is draw in our cross section and put in the things in the terms in the problem that we're going to need to work with. So there they are. And I mean, these are the watershed fluxes. And so this is just an illustration of this type of problem or this particular problem. But in general, if we were doing this, we wouldn't, at this point, we wouldn't necessarily know what the balance is going to be, what the control volume is going to be. So the strategy is take the problem, the different terms that we're interested in, draw a sketch, and then from that sketch, draw in the control volume so that the things that you're interested in cross the boundary of the control volume. Okay, so we do that and we get this formula that we've seen on the previous slide. And we're interested in ET. So we get this solve for ET. And we're given on the previous page, I think this is number 1 on your handout. Great. So we're given values for P as 60 inches per year. And the runoff was 22, I think, stream flow. 22 inches per year. They're the same unit, so we can subtract them and get 38 inches per year. Okay, so that gives us a way to estimate the evapotranspiration over the watershed. Now, it's a simple little math problem, but here's one of the reasons why we might want to do that. So the flow of the stream, it turns out the USGS has a pretty detailed network of stream gauges all around the US. As you're going south from campus, you cross 18-Mile Creek right before you go up a long hill to Tri-County Tech, across the stream right there. And there's if you look off, you're going towards Tri-County Tech and crossing that bridge, you look over on the bridge going the other way, there's a small solar panel, and that's powering a device that is measuring the stage of the stream. The stage is correlated to the flow. So that site is measuring the flow in the stream, and you can get online and check it out, it's within the last 15 minutes. So there's a big network nationwide for making this kind of measurement for free. You can just look it up. Rainfall, there's also extensive measurements of rainfall. It's easy to measure. I'm sure everybody has seen a rain gauge. There's a more electronic one for recording it. So this is even easier to measure than stream flow. Okay, so these two things, easy to measure. Evapotranspiration, this is the flux of a water vapor up in the atmosphere. Not so much, not so easy to measure. Now, there are techniques, there are devices that use what's called a Doppler anemometer, a device that measures the flow of air very rapidly and also measures the humidity. So it can calculate what the upward flux is. Complicated point measurement. Those devices cost about 30 grand, I think, something like that. So much harder measurement to make, and it's also just a local measurement. What we can do with this is we can get an estimate of what the average ET flux is over a watershed. So essentially for free, right? Because we're measuring this stuff and we're extracting that information from the information we already have. So that's pretty good. That's a nice application for the water balance. Kind of leverage measurements and give us some additional insights. Okay. So here's another example. Average, it's same flow or same precipitation, except now we're given the flow in the stream as a volumetric flow. That's CFS, that's cubic feet per second over the watershed area. So the problem still involves precipitation and the runoff here and VT. So the balance is going to be the same that we just saw. But in order to form an equation, we have to have units the same. And this is, if you went online and looked at the stream gauge for the for 18 Mile Creek, you would find that it's in units of a volumetric flow. That stands for cubic feet per second. Okay, so if you use that number, that's not the same units as precipitation and ET, so you can't have an equation. So what you need to do is recognize that the ET and precipitation are essentially what they're doing is taking a volumetric flow and averaging it over the watershed. You know, a rain gauge is measuring the volumetric flow going in here and normalizing it by that area. And that gives you, that'll give you the depth of water in the rain gauge. I just got a new rain gauge at home and it looks like this. So this is like an amplifier. So if you have 1 inch of rain, it's actually like that high because it's normalized by this area. Okay, so what we need to do is get the stream flow and normalize it over the area. And conceptually, it's a little bit peculiar, right? Because we think about this. Here's the watershed. We're measuring the flow right there at the outflow of the watershed. So we've got a volumetric flow here, and we're normalizing it over this whole area. So, conceptually, it's a little bit odd, but that's what we need to do to use it in this balance. So we're going to take the volumetric flow of 72 cubic feet per second and turn it into a flux over the watershed. So remember, flux, little q, I always use little q for flux, is the volumetric flow divided by the area. So this is a volumetric flow, and the watershed area is 40 miles squared. So we need to get this in the annual flux. So let's see, we need 1 mile squared. So the feet will cancel here, and then we need to get this into into years, so. I don't remember how many seconds there are in a year, but I remember how many seconds there are in a day. And. Okay, so. There's the conversion. This goes with that. That goes with that. That seconds goes with that second. The feet squared goes with feet cubed of equal 1, but we end up with feet per year as flux. So you go through, punch it in your calculator, and should get around 2 feet per year. So you could go and check it, but I think that should work out to be right. I wanted to also draw this out and show you a way that I know everybody has done this kind of calculation for unit conversions and that sort of thing. This approach where you write it out as just a single fraction, you write out all of the numbers, and when you do a conversion, you write it out here as a ratio that equals 1, and write out the units. And then you go and cross everything out. Takes up a little more space than some ways, but you see everything and you cross out all the units. And this is going to be the best way for doing calculations like this and avoiding errors. What I see a lot of people do is have a fraction up here and a fraction down here, and it gets a little murky about just what cancels out with what. I also see people doing this without writing the units out, just putting the numbers down. And you can get the right answer doing it that way, but you can also make mistakes easier by writing the units out and then using the units to cancel out. It works as a check to see if you've missed something. So I would urge you to use this kind of approach for doing this kind of really for doing all types of calculations. But they involve arithmetic and units. Okay, so that's one approach where problems involve precipitation, ET, and runoff. But we have other problems that involve other domains, and we can do this volume balance approach over a variety of different domains. And here's one example. So this is a balance over the beta sum. So this is the beta sum here. And we can do a couple of different versions of the balance on the beta sum. So one way would be to take the control volume at the water table and then above the ground surface here. And so this balance is going to be, let's see, precipitation is coming in here. ET is going out. Recharge is going out. Overland flow is going out. The subsurface storm flow is going out. These guys are coming out here. Okay, so that's going to be one approach. So if we have a problem that is involving these components, we draw in the control volume and we get equations like that. So here's the summary, and P equals ET plus FT plus RE. So in the summary there, what I've done is lump these two together. This is overland flow and subsurface storm flow. So those are the rapid flows that occur during or right after a rainstorm. And here in the red on the slide, I've lumped those together as ST or storm flow. So either way works. And I also have this piece of pie here. And what happens is that the runoff, this is our piece of pie, this is all the precipitation coming in. And what we see here is that the runoff is partitioned into, looking at it this way, recharge, and that should be ST, storm flow. Okay, so these three components are shown here. And this fraction may change depending upon how much of what fraction ends up getting into the aquifer, or what fraction ends up going to the aquifer, and what fraction ends up being rapidly shed off the landscape as storm flow. Okay, so that's one way to think about the vadosome and the control volume. But we could change it and move the control volume down here to the ground surface. So when we do that, things change a bit because we don't have precipitation going in anymore necessarily, because not all the precipitation is going to cross the ground surface. Remember, we had some interception, have overland flow. Those aren't going to cross the ground surface. So if this is where the control volume is, we have the component that's crossing the ground surface would be infiltration. And then we have subsurface storm flow that's going to come out, and recharge that's going to come out. And the trees have their roots in the subsurface. So evapotranspiration, most of the evapotranspiration is going to be from the subsurface, from the shallow soils, as the tree roots get it and bring it into the atmosphere. So we would include ET here. Yeah. So there's the balance. So infiltration coming in, ET going out, recharge going out, and subsurface storm flow going out. Okay, so here's another problem. This is in the handout. Well, this is getting a little more complicated. We've got rainfall, recharge, overland, subsurface, and we want to know what ET is. Okay, so those are all the different components. And this approach here is the Troyan sketch and include all of those. think that's got all of them. So they're the different things. This is what we're after. These are the ones we're given. So we can draw in the control volumes that has all of these things crossing like that. So that's that first Vado zone control volume. And we get that P equals ET plus O SS recharge. So we solve for ET. And rainfall is 60. So these all have the same units, so we're good with units. So 60 minus overland is 1, minus subsurface is 7, and recharge is 10. So that's 42 inches per year. Yeah.
What was the keyword that let us know we didn't need to use SC or SL?
The keywords that
Like, look, to know to use this one instead of the other one.
so the key is that we take this information and we draw in the sketch. And we draw the sketch in, the sketch has to include the thing that we want to solve for. And it has to include things that need to be there in this particular drawing, in this particular balance. We didn't use the other one because the other one has infiltration, which would be here. So we're not given that. So yeah, so we couldn't do that balance. Okay, yeah. So the way to do it is to draw out the picture. At least that's the way I think is the easiest. Rather than like memorize what each one of these is, draw it out and then draw out the sketch before the blue, and then based on the components that are drawn, put in your control volume. And in order for it to work, you need to have all of the components, but you'll be given the components that you need to work with. Sometimes, if I'm feeling ornery, I might give you more than you need. Like I could have given you on this one, maybe I give you base flow, right? So just because you don't necessarily need to use all of the components that you have, right? When we're getting started, then you know I'll give you the components that you need. But in general, I mean, if you were using this for a project, you would get whatever components you could with whatever methods you could, and then you need to put them together with a valid balance. But you might be getting some components that you don't need. So in general, the strategy though, draw in the sketch and identify the components that are crossing the boundary. Okay, so that's another example. We can go from the beta zone down into the aquifer. And this is another valid region for doing balances. The balance on the aquifer, the simplest one is to go right here. This is a divide, right? So there's no flow going in this direction right here, right? Because the flow on this side goes that way and the flow on this side goes that way. So this is a no flow boundary. And if we have a control volume that looks like this, then we've got recharge coming in. And base load going out. And in this sketch that we have, that's riparian ET. So this is like a, sometimes right down near streams, there's a willow tree. And they're special trees that live near streams that can go and pull water out of the saturated zone. The trees up here don't do that. They don't have roots that go deep enough. So that's why I included this as a separate entity. But often, frankly, this is small and it's ignored. So we'll ignore it here. And then we have really a pretty simple balance. The recharge coming in is equal to the base load going out. Now, we often don't know where this is. So we may put the boundary right here. And then we can have the groundwater. We could draw it like that. And then the balance is going to be recharge coming in is base flow plus GW out. Okay, so if I set it up like this and there was actually groundwater coming in, what's going to happen is this would end up being negative. So we could also draw the boundary out here, in which case there actually would be groundwater going out, in which case that would be positive. Okay, so these fluxes can be positive or negative depending on if it's going in or out. Although this is really, the groundwater is really the only one, for the most part, where it'll be changing sign. Okay, so that's the balance on the groundwater or on the aquifer. There's the one where you have groundwater out, there's 0, and there's groundwater coming in. Okay. So now let's go ahead and do this one. Okay, so here's our watershed with an aquifer, and we're gonna put in things that were given: precipitation, recharge, overland flow, ET, subsurface storm. Okay, and baseline. Okay, so those are the things that were given. And we need to draw in the control volume. We need to pick a control volume that has things that'll be complete. So if we use the control volume on the aquifer, where we're not given it, so we'll assume that the groundwater inflow is 0. So there's the control volume, and we have okay, so we're given all this other stuff, but it's all outside of control volume. We don't really need it. So we can just calculate the base flow flux directly, and it's equal to the recharge which we're given. So we're given a variety of things here, but we don't need these 3 or these 4 terms to get what we're interested in. Okay, so there's an example of case where you're given more than what you what you need. Okay, now the final component that we're going to be interested in will be the stream. And so here's the stream. We draw the, we got base flow coming in. We got subsurface, overland. Okay, so those are the things that are going on with the stream. Getting a little crowded down in there, but we draw in the control volume. Then the balance is going to look like this. Base flows coming in, overland flows coming in, subsurface storm flow is coming in, and then what's going out is runoff. We might also write this like this. The base flow plus the storm flow is equal to the runoff.
Is B going up?
B is going up. B is the groundwater discharging up into the stream bed. Okay, so this has given us some nice insight. It says that the flow in the stream has components from the groundwater as base flow and components from the shallower depths, the storm flow. So one way that we use this is with analyzing stream hydrographs. So if you go to the that site for 18 Mile Creek and check out the flow in 18 Mile Creek with time, it's going to look pretty much, it's going to look a lot like this. So this is a year here. No, that's not. That's 2 months. Okay, so we have every month or every couple months we have this peak. These are storms, floods essentially when the flow increases a lot. And what we can think of then is that the flow is equal to, here's 0. So there's this part, the green dashed line, that's the flow that is independent of the storms. Okay, so if we take this and if I take the blue line and subtract off the green line, then I get the red line. Okay, so that red line, it's going to 0 essentially here. But this is the storm flow here. And then that green line right there, that's the base flow. So you can see at any given time, the flow in the stream has this much base flow and that much storm flow. And during a storm, it's many, many more times more storm flow than base flow. But during times like this would be like, like right around now, there's hardly any storm flow or 0 storm flow. It's all base flow. So all the flow of the stream is coming from groundwater discharge. Okay, so this water balance maps out directly to analyzing stream flow hydrographs. And there are a lot of applications for doing this kind of separation of the base flow and the storm flow. And then you can do various analysis once you have that. Okay, so I gave you a handout with some practice problems. We've done a few of them. I want you to do the rest of them. Check it out. If you want to go to the course, the module, there's the answers there. So go and work them out yourself. Draw in a sketch, draw in the control volume, come up with an equation, and then check it out. Make sure that you're on track. I think the answers, I think there's also a little video that shows how to do it if you wanna do that. Okay, so practice that, we can move on to the next topic.
Yeah.